So we've talked about classification. Now let's talk about prediction. Actually, it's a little bit simpler to talk about because it's almost identical. And in fact, behind the scenes, what's going on in classification is to effectively attach numbers to classes and then make a numerical prediction and then seeing which number that's closest to. So it's the same basic usage. We give some inputs and some outputs, and these inputs could be complex, rich, multi-dimensional things like images or sounds or vectors of numbers, but in this case, I'm just putting one number in, one number out. And then we call predict to make it clear that we're after a numerical prediction. So this isn't a class called 1.3, but actually it's a number that is just a little bit different from 2.4, not a completely discrete different group called 2.4. And we get a predictor function out that works just like our classify function in previous examples. I give it an unseen piece of data and it makes a prediction that is going to be numerical. So it doesn't have to be any of the numbers it's seen before. It can be any number above, below, or in between the examples. Now, this is, of course, the most trivial example I could think of. And you could equally have done this by doing standard linear regression. And in fact, if you look at the method that is chosen, it's done exactly that. One dimension in, one dimension out, a bunch of numbers that are vaguely in a straight line. It's done a linear fit to that. Now, as well as using the prediction just like before, we can delve in a little bit deeper, but it doesn't make sense to ask for the probability that this is correct because it's continuous. It's guaranteed to be not exactly right. So the question is, how far out is it likely to be? So here what we get out is when we ask it for the accuracy, instead of a probability number, what we get is a probability distribution. So a whole range of numbers. In this case, a normal distribution centered on just above 2, which was its best prediction, with a standard deviation of a little bit over 1. And if we plot that, we can see exactly the range of possible values that it believes that it can get from this data, that its best prediction was 2, but there's a reasonable chance it could be anything up to about 4 down to nearly 0 before it becomes an ignorable probability. So let's do a slightly richer example that is a little bit more multidimensional, where the machine learning becomes much more useful. This is another classic example. This is a data set of Boston house prices. You'll see when we look at the data that the data is rather out of date. I don't think you'd get a house in Boston for these kind of numbers anymore. But this is a data set that was collected some years ago that had a dozen or so input values that might have predictive value for how much a house is worth. So there is the crime rates in the area, or things like how accessible the roads are. A whole bunch of things to do with the part of town that you're in that might affect house prices. So let's have a look at a sample of that data. Here are the numbers. So there is a number associated with each of these inputs that affect our prices, and then a value in thousands of dollars. So this flat was a $22,000 flat. So this is exactly analogous to this trivial example we did a moment ago. Input and output is just that we've got a 10-dimensional or so input now. We use it exactly the same way. We just say predict on that data. It builds our predictor function. And now we want to see how well that has performed. So just like with classification, we want to compare it against a training set that we held back. So we've got this test data that has unseen examples, and we'll produce a predictor out of that. Now, again, because these are continuous numbers, the tests that we used, like accuracy and confusion matrix before, they're not so appropriate because they're geared around absolutes of in the right class or not. So one of the most useful is a comparison plot, which is just plotting the input versus the output value. So here we have a data point that was predicted to be a $15,000 flat, but actually was a $9,000 flat. So the perfect prediction here is everything. It doesn't matter how spread out they are, but they should all be along the dotted line. So at a glance, we can see here that it's done a fairly good job for houses in the middle price range. That for very low-priced houses, it has a tendency to underpredict, and also for very high-priced houses, it's having a tendency to underpredict. So maybe this is a a useful thing for typical houses, but if we were using this as some kind of automatic estate agency tool, we should call in a valuation expert for anything that's outside of the $10,000 to $35,000 range. Another sad measure would be the standard deviation, which one can think of vaguely as being the kind of plus or minus number to attach to predictions. So one could vaguely think of this in terms of each prediction is plus or minus $5,500. So that's typically how close we're going to be, and is really, to some extent, the measure of how far from the line the top points typically are. And just as we did with classification, we can look up things like best and worst predicted examples. So here's our worst predicted example. Here's the inputs and the actual output, and we could compare that to, I guess we could put that straight into the predictor, which was called P was our predictor function, and say what's P of that value, and see that its actual prediction was 20,000. So that's why it's come out as the worst prediction, because 20 and 50 are quite a long way apart. So just like with the classification, one of the things that the automation of the language provides is to be able to deal with all kinds of different input types. So I'm going to do a visual example here to show that it's not just kind of numerical in and numerical out. The Wolfram language has all kinds of visualizations. So for example, I can ask for the angle of gauge of some number and get a picture out. So I'm going to generate those pictures as pictures and then use them as training examples so that we can start predicting by looking at an angular gauge what it's reading. So let's make a training set here by making a whole bunch of random angular gauges with their associated value. And if we look at 3 examples from that training set, once it's generated all of those pictures, which will take a few seconds. So here's 3 examples. So this is the correct value on the gauge, and here's what the picture looks like. But this training set's just like all the others we've seen, input and output as a list of data. So we just say predict on that, just like we did with anything else. So the task becomes, with most of these machine learning jobs for the language, is just to get it into this shape in the first place of a list of inputs and output pairs. So it'll take a few seconds to analyze all of those pictures and look for the features that it thinks are best predictor. That presumably it's going to figure out that these numbers don't help much because they don't change between one example and another, but the red line does help. And we've got a predictor function out, and now I'm going to make a little interface to let me play with the predicted value. So here I've got an angular gauge that I'm going to use as an input. I'm going to drag the hand around, and here's its predicted value according to the predictor. And hopefully, as I drag that around, you'll see that the right-hand side mirrors what's going on the left-hand side. And actually, this is doing a little bit better than usual. You can see a little glitch there where it jumps around, where it's become, the prediction hasn't been quite as perfect, but on the whole, it's managed to make a good predictor. Of course, this is a very controlled example. Real-world image processing needs lots more than 100 data points because the image is rarely so clean. You always have things going on in the background and lighting changes, and the camera is not always in a perfect position and so on. So you need more data so that the key features can be picked out from that.